Greetings and welcome, friends. Today we're going to put our vectors to work, which is kind of funny because I'm going to define what work is a little bit later. But seriously, folks, oh man, how are you even going to learn after LOLing right now? You guys are all raffling. You can't quite. I wish I had video of all my students just raffling right now. But internet friends, once you're able to sit back in your chair, we're going to talk about applications of vectors. We're going to put them to work, as I said. And here's our first little example. It says, two trucks are pulling a stump. So I'm going to draw a picture of a stump. Let's see, this will be amazing. So here we go. Here's my awesome little stump. It's a sad stump, actually. Man, what? Here we go. Whoop, 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 whoop. There's my awesome stump, right? So I imagine that it's something like that, right? So one truck is pulling the stump north. All right, I'll assume north is up at 1,200 newtons. Okay, yeah. And another truck is pulling the stump east at 1,400 newtons. All right, so they're kind of meeting at a 90-degree angle there, so to speak. And it says, what is the magnitude of the resultant force, and what direction is the resultant pulling at? Okay. Also, I made up these numbers. I have no idea how many newtons a truck can apply on a chain to a static object. Oh! So the first thing I'm going to do is I'm actually going to, so this is kind of like the real life drawing, but let's actually draw this kind of in terms of vectors being added together, because these two vectors are combining their forces simultaneously. So I'm going to think of that as vector addition. So I'm going to kind of draw like a little triangle method sort of thing. So this will be 12 hundo, this, and then kind of tip to tail it, you know what I'm saying? 14 hundo, and then the resultant force is the one like that. So there's my resultant. Something like, right? So I'm going to be looking for the magnitude of this resultant as well as the theta of this resultant, right? From the horizontal or from east maybe. I don't know. I guess technically I could also define it as an angle from, east of north or north of east, whichever way you want to call it. But so that's what I've got going. And these happen to meet at a 90-degree angle. So this is the resultant force that I'm looking for. In order to find that resultant force, the magnitude of it, what do you think I could do to find the magnitude of R here? Thoughts? Yeah, definitely. Yeah, let's not complicate things. Let's just... so the magnitude of the resultant squared is equal to 12 hundo squared plus 14 hundo squared. So that's going to equal the magnitude of the resultant is going to equal, well, you'd root both sides, and we'd only really care about the principal root, or the positive one. Turns out that all adds to be 3, 4, 1, 2, 3, 4, 5 zeros. I think that's one too many zeros. Yeah. So what's that, 3.4 mil? Yeah. And if I square root that, it's going to tell me my newtons. I'm going to get around 1,843.91 newtons for my resultant force. So notice that it is not purely, say, 2,600 newtons. Okay? How could I have gotten those trucks to output 2,600 newtons on the stump? Yeah, I'd have to pull them in like the same exact direction, right? Two trucks pulling exactly in the same direction. Or I could get a larger overall magnitude, even if I had them pulling in directions closer to kind of like the same direction. The more narrow I make this angle here, the more of that force would be combined in a single direction, so to speak, right? So there's my resultant. How do I find my angle? Well, in my little right triangle here, I'm actually going to call this alpha. And from angle alpha's perspective, actually I might even label that with a double arc, how about we? What leg is the 1200? Adjacent, and what leg is this one? Opposite. What trig ratio compares adjacent and opposite? Tangent. So I'm going to say tan alpha would equal opposite, the 1400, divided by the adjacent, 1200. So alpha is actually just going to be the tan inverse of that, right? And I end up getting 49.40 degrees. All right, so that's alpha. What if I wanted theta? Yeah, 90 minus that, I actually would get 40.60 degrees for theta. So if I wanted to communicate that in some sort of like direction, I would say that the resultant force is 1,843.91 newtons at 40.6 degrees north of east. I could describe that. North of east. Right, so that would describe what direction that's going. All right, so that's the idea. So in this case, this ended up just being like a little bit of Pythag, a little bit of trig, and it wasn't that bad, right? So this is kind of, well, it'd be nice, I imagine. It'd be nice. So, so we can use vectors to represent different forces on objects, and this is often what physicists do, you know, to represent all sorts of different things going on. It actually, they'll even do it for statics, which is a field of physics where there's no motion occurring, where it'd be like, what are the forces occurring to all the trusses on a bridge? And hopefully our bridge isn't moving, because if our bridge is moving, then that's probably bad news for our bridge, right? Like, we want our bridge to be static, right? Non-variable, that it's staying in one location. However, there are still forces that are exerted on it at all times. So let's see, the definition of work is going to be needed for this next problem. Work is equal to my force vector that's exerted on an object, and I dot product that, okay? So notice that's not cross product. I dot product that by the displacement vector of the object. So displacement is going to be the direction and distance that the object is moved as a result of my force. All right. Or in this case, it's actually not as a result of our force, but the force still ends up doing this work to the object. So we're actually not interested in how much work Alvaro does, but how much work gravity does, which, right, yeah, work done by gravity. So, both of these are vectors. Dot producting them is going to equal some number, remember. So just like some number, some scalar. And that number, in the case of this problem, is actually going to be measured in foot-pounds, is what it'll end up representing. So, let's draw a picture of this. So Alvaro works for a package delivery service. He is pushing a cart full of packages weighing 100 pounds up a ramp 8 feet long at 25 degrees. So, so my displacement vector is going to be my ramp. All right. And it's 8 feet long, so that's the magnitude of the displacement vector. All right, so 8 feet. And the angle of the displacement vector, or its direction, is the 25 degrees, right? So that's where the object traveled, all right? Now, as far as the other vector, force due to gravity, which direction is gravity going to be pulling this cart? downward force. All right, so here's my gravity vector. And that is going to have, yeah, it's a sad looking G. So there's my gravity vector, and that's actually pulling at negative 100 pounds, or 100 pounds in this direction, right? But we'll end up calling that negative 100 in a minute when I consider it as an ordered pair with a y coordinate. All right, but its magnitude is still positive 100. So so there we go. There's our sketch. And so my object ends up moving up a ramp 8 feet, but this is continually putting 100 pounds of force on it. And it says assume friction's not a factor. That's nice. Thanks for helping us out there. So what I'm going to do is first I want to represent this displacement vector as its kind of horizontal and vertical components. So I could call, I'll just call this x and y, right? I could have called that d sub x and d sub y if I wanted to break it up like that. So what could I do to find x and y? Sine and cosine. X happens to be the adjacent. The displacement vector's magnitude 8 happens to be the hypotenuse. So I could say that cosine of 25 degrees is going to equal x over 8, or I could refer to that as the magnitude of vector x. And then for y, I could say that sine of 25 degrees is equal to the magnitude of vector y, the opposite divided by the hypotenuse, which is 8. So I'd solve, multiplying both sides by 8. I end up getting magnitude of vector x is 8 times cosine 25, which is going to be about 7.2505. And 8 times sine of 25 is going to be 3.3809. And these are measured in feet and have their directions accordingly, right? So if I wanted to represent this vector d as an ordered pair, that is the vector 7.25, comma 3.38 is the ordered pair for that vector. And if I want to represent my gravity vector as an ordered pair, what is the horizontal component of my gravity vector? For the gravity vector. This is still, these were for the displacement vector. Well, for the gravity vector, if I tried to draw a triangle representing this as its resultant, right, it's not going left or right. So the horizontal component is 0. And the vertical component, it's going down 100. Root 100 south. So let's see, work. That was kind of a loop-de-w I drew first, and I was like, that doesn't feel like a work variable. Work is more serious than like loop-de, so it's more pointy, it's edgy, it's got harder lines. You know, that's what work should be. So I'm going to find the work, I multiply my force by my displacement. So I would just dot product these guys. So 0, negative 100. Dot product with 7.25, comma 3.38. Now remember, I'm expecting this to equal a number. And so I'd have 0 times 7.25 plus negative 100 times 3.38. And that's going to equal negative 338 foot-pounds. I need an L there, don't I? So that is the amount of work that is done by gravity over time, which I do realize, like, that sounds weird thinking of gravity doing work, but go talk to a physicist. So there's our first two concepts where we can apply vectors in kind of those ways. So this one had two forces. This one had one force and a displacement vector, and we're able to calculate work being done. The next thing I want us to think about is actually going to be kind of in that realm of statics that I was describing, in which actually I might even skip down to this first. Equilibrium occurs when forces balance one another, all right? Or the sum of the forces at equilibrium add to zero, all right? So there's no resultant force, or the resultant force is a zero vector, all right? And if I was to draw tip to tail sum of all of my vectors, they would actually form a polygon, meaning it would end where it started, right? So all of those vectors all combined result in no actual overall change on our scenario. So that's described as an equilibrium. So things that are at equilibrium would be, for instance, the screen that we have our work projected on is not moving, but gravity is pulling it down and those chains are holding it up to the ceiling, right? So that would be at equilibrium. Or bridges, like I mentioned earlier, stuff like that are at equilibrium. Are you still writing? I'll let you finish writing. So equilibrium. So for instance, when we were playing tug of war the other day, you had two opposite forces, and if there was no change in the location of the knot, we would describe that being equilibrium, and that has nothing to say regarding the each individual force. They could have been very large forces, they just happen to have no overall outcome. But you can also have equilibrium that are not parallel forces to one another. I mean, what if we had like the freshman class pulling this way, the junior class this way, and maybe like the senior class pulling this way? And somehow like all three of these actually would end up as, right, single, no change resulted is what we'd be describing. So, all right, so let's look at this situation. It says, Miss Davis is hanging a sign for her restaurant day. The sign is supported by two lightweight support bars. I have those drawn in green here. I also drew this at a perspective drawing, so I hope you appreciate my artwork. Look at this awesome brick that I've got going on here. It says if the bars make a 30-degree angle with each other, yep, so you could just draw, right, that, something like that. So I first draw the realistic situation, and then I draw the vectors representing them, okay? And the sign weighs 200 pounds. What are the magnitudes of the forces exerted by the sign on each support bar?
What are the two bars?
The two green ones. So imagine like there's a horizontal bar and then kind of like an angled one. So they'd be like attached to the building, keeping the sign from like just falling or levitating in free air. So yeah. So if I want to draw this situation, you could actually think of it as, now let's figure out the sign's vector first. What direction is that vector pulling? Down, right? It's pulling down 200 pounds. All right. How about this top bar? What direction do you think that has to pull in order to counteract? Is it pulling? Is it pushing towards the sign or pulling away from the sign? It's actually, yeah, it's pulling away from the sign. So this vector is like this. I'll label that force 1. And now this one is a little bit trickier to think of. Imagine if I cut this. Which way would this swing? Would it swing out this way or this way? Yeah, right? It would like pivot towards the building. So this vector, in order to counteract that behavior, is going to have to push out. All right, so it's acting as like kind of like a stiff arm in football when you're playing Madden. That it's pushing out this way. Okay, so that's not necessarily extremely intuitive, I don't think, but it has to be. Yeah. Right, so this object is all kind of being represented here. Now, if I want to draw this as the sum of these vectors to one another, and I want to tip to tail this, that's going to look like this. So I'd have force 2, I'd have force 1, and then I'd have the pounds due to gravity, and they would end up exactly at the same point. All right, and that's the idea of what a equilibrium looks like in terms of our tip to tail method. So we'd have force 2 is here, we've got force 1 here, and then we've got, I don't know, force due to the weight, maybe force FW force. All right, so notice that it ends back where it started, so there's no change, there's no movement on this object because all of those are at equilibrium. They're holding the object static in location. So if I want to now figure out some of these values, let's see, what do I know? I know this magnitude. This magnitude is 200. What else do I know? I know this angle. What's this angle? 30 degrees. And that's all I know. So if I want to find out the magnitude of force 1 from this 30-degree angle's perspective, this is opposite, this is hypotenuse, that's going to be a sine, a sine problem, am I right? Oh man, internet friends, they're all raffling again. Oh man, guys, calm down, please. We've got to learn in this environment. Oh my goodness. I got to stop being so hilarious. So let's see. Sine of 30 degrees is equal to 200, the opposite, divided by the hypotenuse, so over the magnitude of force 1. So to solve that, you could multiply both sides by force 1 and then divide by sine of 30, and you'd end up getting the magnitude of force 1 is equal to 200 divided by sine of 30. Actually, wait a minute. What's sine of 30 equal to? Hand triggers. A half. So what's 200 divided by a half?
400.
400. Right? So 400 pounds of force is being exerted by this one bar, which notice is twice as much as the weight of the sign. Right? If I just had it like hanging from a ceiling or something, or right, that could have just been 200, but it actually has to sustain a lot more because of the angle. All right, let's figure out force 2. Force 2 from angle 30's perspective is which leg? Adjacent. Compare that to opposite, let's say. So let's tangent that. So tan of 30 degrees will equal 200 divided by, let's see, the adjacent is the magnitude of force 2. So the magnitude of force 2 is equal to 200 divided by tan of 30. Tan of 30 is going to be 1 over the square root of 3. I believe that's 200 times the square root of 3, but we'll just write it as 346.41 pounds. And actually, if you ever do have an opportunity to study statics, or if you've ever built a popsicle stick bridge before, you might know that your different joints are actually, some of them are under compression and some of them are under tension. All right. So for instance, in this case, this one I believe would be under tension and this one would be under compression. All right. So it's actually possible that this one could be a rigid beam and you could actually replace this with a chain. Where chains can't be under compression, right? I can't, like if I push on that chain, it's just gonna like crumple together, right? That's not gonna be helpful. But since it's under tension, the chain will stay kind of in its longest form and be able to sustain that force. So I just want to point that out, like you can eventually figure out even that and be like, oh, so I just need a chain that can sustain 400 pounds, and then I need some sort of beam that can handle compression of 346.41 pounds. And actually different materials end up being able to have different compression limitations versus tension limitations. Not just in the instance of the chain. But. So there you go. Let's look at the last example. Another equilibrium problem, or so we hope, until Zorro goes swinging on our chandelier. Well, it just says it's a lighting system, but I'd like to think of this as a chandelier of sorts. So it says it's supported by equally, all right, so that's important, by two cables suspended from the ceiling of the theater. Now, if it's supported equally, could it look like this with 140 degrees? No, like that wouldn't be equal for some of them. One of those would be under much greater stress. So if it's equally, I imagine that they kind of have to be somewhat symmetric to one another, like so. And let's see, so I've got, those are going to be pulling this way and this way, and those are going to be under tension, and that's why it actually described those as cables a second ago. And then we've got the weight of the object pulling down, all right, something like that. And information we know that this is 140 degrees, and we know the weight of the object force is 950 pounds. Now in this current sketch of somewhat of a flux capacitor design, this isn't actually helpful for doing trigonometry, so I'm actually going to redraw this now as the sum of vectors. All right, so tip to tail method. So let's do, I'll do this one first. I'll do it over here. It's all right. So I've got like this one here, and then I'll do this chain. Tip to tail would be back like that. And then I've got the weight of it, and it's at equilibrium, so they would all have to meet. And what I know here is that this is 950 pounds. And now let's see. I know that these are equally under pressure, so this is actually an isosceles triangle. And let's see, can I figure out how to describe these two angles? I know they're congruent. Well, let's see, I think I might have a couple ways of doing it. What is this angle here going to be? Right, this would be 40 degrees. All right, this angle will actually correspond to this angle here. All right, so this is 40 degrees. And if these two are, if this is 40 degrees, what must these two be? Oh, and I think, Sam, that might have been what you were saying, right? Maybe. Ooh. Well, right, all of these add up to 180. 180 minus 40 is 140, not coincidental. Divided by 2 equal, right? Equal angles, so those are both 70 apiece. All right, so the magnitude I'm looking for is either this or this. I could just call those some variable x or f for force or whatever I want to describe. And let's see, this is a non-right triangle. It's just, this isn't right, man. What do I do to solve for x? Would the law of cosines be helpful? Hey, I've got a pair of angle and opposite sides, so I'm actually interested in law of sines. A over sine of A equals B over sine of B. You might remember law of sines, good stuff. So let's plug this in. X over sine of 70, all right, because that's opposite of each other, a side length and an angle, is going to equal 950 over sine of 40 degrees. So to solve for x, I could multiply both sides by sine of 70. Right? And I'll get x is equal to, this is what I'd plug in my calculator, 950 times sine 70 over sine of 40. So x is about, here's a calculator. Let's see, am I in radians or degree? I am in radians. So sine 70, close parentheses, divided by sine of 40, close parentheses, multiplied by 950. And I get 1388.8071. And this would be measured in pounds. Pound it. I think we got this right. So, So not too shabby, friends. So, big idea with applications of vectors. If the resultant force is 0, our situation is an equilibrium. So, thanks for watching. Adios.